We have come to the last macromolecule. We already covered nucleic acid. Then we went on to cover protein and its subtopic of enzyme. And recently we looked at carbohydrate, and now we are looking at lipid. So lipid is considered oils and fat. Oil is in liquid form while fat is in semi-solid form. And you will realize that oil normally comes from vegetable or plant sources, while fat comes from animal sources. You also have some vitamins as well as steroidal hormones. These vitamins has been included as lipid simply because it's non-soluble in water, and that's why it's been included in lipid. The vitamins concerned is the A, D, E, K, and the hormones are the steroidal hormones such as the testosterone as well as estrogen. It is not polymeric because it's around 20 carbon hydrocarbon chain. It's not like 50 or 100 hydrocarbon chains. And then it is also able to contribute in the making of the biological membrane, that is the lipid bilayer or biological membrane. And therefore, apart from contributing to energy production, it is also in the making of the biological membrane. In terms of the importance of lipid, it is for energy storage, and the component relevant for energy storage being fatty acid as well as triacyl glycerol. You will see that triacyl glycerol is actually made up of fatty acid. And then you also have a structural making the cell membrane, which can be contributed by phospholipid, glycolipid as well as sterol, which happen to be cholesterol. And also somewhat in a different class, that is other lipid, is the vitamin A, D, E, K. Now we look at the components of the lipid itself, one component to the other. We start with fatty acid. Fatty acid is the simplest form, and it actually makes up triglyceride, even phospholipids. And then it has at one end carboxylic side, and then the other end being hydrocarbon chain, the long aliphatic hydrocarbon chain. It is normally 10 to 20 only. If there is more than 20, then it is synthetic rather than being natural. And then you have most common one, palmitic acid, 16 carbon, stearic acid, 18 carbon. And mostly even numbers like 16, 18, 20, but they are also odd chain fatty acid in nature. So here shown the diagram on the saturated as well as unsaturated. The unsaturated basically inclusion of one or more double bond, and because of the double bond it will bend, and this bending is referred as kinks. So more information on saturated fatty acid. It only has carbon-carbon single bond. It is highly flexible and to be found flexible when it is fully extended. And the melting point increases with chain length, and this one I will demonstrate later on how as the hydrocarbon chain increases two at a time, you will see the melting point increases, and then when there is a double bond, the melting point actually decreases. Here given examples of stearic acid or stearate, which has 18 carbon in total. Next, we look at unsaturated fatty acid. It has to have a double bond, either one or more double bonds, and then it is considered polyunsaturated if it has more than one double bond. And here the term comes essential fatty acid. This essential fatty acid is fatty acid that the organism has to obtain from diet. When it comes to human, we cannot make fatty acid having double bond at location 12 and beyond. So because we do not have the desaturase enzyme, and therefore we have to obtain it from the diet, and hence it is referred as essential fatty acid, just like essential amino acid, which you need to obtain from the diet. So you have the first double bond at C9, and then it jumps to C12 and then C15. Okay, as shown here, it jumps in 3 carbon onwards. And given example in terms of diagram, comparison between oleic acid as well as linoleic acid. Oleic acid having one double bond at location of 9, while linoleic acid having two double bond at location of 9 and 12. So now we look at this omega-3 fatty acid term. It is a term which is a very old term. Nowadays, the nomenclature or naming is actually done by the carboxylic end of the fatty acid. But this one, omega-3 fatty acid, is from the methyl side or the hydrocarbon, the end of the hydrocarbon chain itself. And it is basically found in fish oil, corn, and also olive oil. These oils have been found to be very useful, and it benefit the person of avoiding having heart disease. This one, the Eskimos, they take fish oil, and also Mediterranean countries such as Italy, they take a lot of olive oil, and it was studied and found that these people have low levels of heart disease, and this is because of the omega fatty acid, omega 6 as well. And here given the example where the omega 3 comes from the methyl side, you just count 1, 2, 3, and that's omega 3 fatty acid. So now we move on for more information on unsaturated fatty acid. It is cis type. There is also trans unsaturated fatty acid, but it comes about because or man-made rather than found in natural. How it comes about is due to hydrogenation, where they want to make the oil become, say, palm oil become margarine. In the process, the byproduct is actually trans fatty acid, but trans fatty acid has been known to be bad for health, so must be careful in the hydrogenation process itself. And then the unsaturated fatty acid will, because of the double bond, it will bend, and this is referred as the kinks. And then it is not packing very well compared to saturated fatty acid. Because of the not packing very well, it is having a lower melting point. And if the melting point is below room temperature is considered like 25 degrees Celsius. So if it becomes like, say, 20 degrees Celsius, then it will melt. Then it will be in the form of liquid rather than semi-solid. So normally all these unsaturated fatty acids are found in plant or vegetable oil. Therefore, all these plant or vegetable oil are found as liquid rather than semi-solid. So you can see here that you can see the saturated fatty acid, it's straight, while the unsaturated fatty acid has a kink here. Okay, this kink will actually cause a space, a large space, which has no interaction with the neighboring fatty acid. Therefore, it's not packed in compact way and easily broken. Therefore, the melting point is actually lower than the saturated fatty acid. So this table is a good indicator of the melting point that is reduced when there is introduction of double bond, and also increase in melting point when the hydrocarbon chain increases. So you can see here, as you go below this table, you can see the melting point increases because the two carbon at a time being included. And then if you look at the inclusion of a double bond, especially this 3, the 18 carbon, you can see as you increase the double bond, the melting point also decreases. And then if it is 25 degrees Celsius in the room temperature, meaning those triacyl glyceride or those oil made up of this 18 carbon, which has already having double bonds, will be in the form of liquid because it melt, and that's the physical form that is for the oil. So next we look at triacyl glycerol. It's also known as triglyceride, also in the abbreviation of TAG, TG, and then it is made up of ester bond connected. The fatty acids are connected to glycerol. Glycerol is an alcohol. It has 3OH, and that's where the connection will happen to either same type of fatty acid or different type of fatty acids. Okay, so it's mixed. Then you have example given, that is stearic acid, linoleic acid, as well as palmitic acid connected to this mixed triacyl glyceride given. So a bit more information on triacyl glycerol. It is the most abundant class of lipid in animal. Unfortunately, it makes the fat of a person or a fat of the animal. Therefore, it can lead to become classified as obese or overweight. And then the melting point is determined by the unsaturation. More double bond included in the triacyl glycerol, the fatty acid, then it will become lower in melting point. And then what is generally known, plants have more unsaturation. That's why vegetable as well as plant oil, they be in liquid form rather than in semi-solid, which is found for animal. What is the most important function? It is for energy reserve as well as insulation. Energy reserve, it can actually provide in the same weight ratio. You can get more energy from fat compared to carbohydrate, simply because the fat is all in reduced form while carbohydrate is in oxidized form. And in terms of insulation, is referring to, in the cold climate, you want to keep warm, and it seems fat around the person's body actually keeps the person warm as well as an insulator. And then where the triacylglycerol is stored is in the adipocytes. And then when required, unfortunately, it has to travel from adipocyte, the fat cells, to the muscle cell through the bloodstream, and then only can be oxidized to get energy. So now we look at phospholipids. It is negatively charged because of the phosphate that is found there, and also could have positive charge or a polar component, which we will see in a while. Can be called as glycerophospholipid because of the glycerol that is involved in connecting the fatty acid as well as the phosphate group. And then it makes up the lipid bilayer of the cell membrane, so it's contributing to the structural part of it. And the glycerol 3-phosphate, which is happen to be found in the glycolytic pathway, the intermediate or metabolic pathway, can be actually used as a precursor to build this phospholipid by adding fatty acid as well as the phosphate, and also to the phosphate a polar group. And this polar group is the one we will see in the next slide. So here you see the glycerophospholipid being shown, where it has the fatty acid connected to the glycerol backbone there. This is the glycerol. So two fatty acid, and then you have also the phosphate group connected to the X group. This X can be either one of these, that is serine, choline, ethanolamine, or inositol. So next we look at the example of phospholipid. Given here is phosphatidyl inositol, where you can see the glycerol and the two fatty acids, either same or different type. Then you have the phosphate there, and the X group is the inositol, or somewhat a monosaccharide. This contributes in the cell membrane as the lipid bilayer, also in the cell signaling, where it can get cleaved and trigger the inflammation effect in the cell membrane. Here given phosphatidylcholine, also contributing to the cell membrane, the lipid bilayer, but compared to the other one, this one does not have the monosaccharide, but in place is this choline, and this choline has positive charge while the phosphate has negative charge. Due to the X group, this X group either being carbohydrate having lots of OH group, or being a charged group, it will contribute towards the whole phospholipid itself, whereby the charged group as well as the phosphate group, which has a negative charge, will be considered as polar, liking water, because water having negative charge and positive charge will be attracted to this negative or positive charge, or even the OH group, and therefore this is considered polar region, this one here, so same as that. And then all the other component having hydrocarbon chain will be considered as non-polar. So that's why you have polar as well as non-polar, also referred as head and tail. So if just now we look at phospholipid, now we look at glycolipid, where the phosphate group is not there, but in place there is something still considered to be polar because of the monosaccharide as well as disaccharide, or uh, you know uh, carbohydrate, which is derivative type, contributes to the polar region. So you have still the non-polar as well as the polar head group. So in terms of it could be monosaccharide, or it could be disaccharide, as well as contributing in the buildup of membrane of the chloroplast. Next, we look at Spingolipid. Spingolipid, unlike of phospholipid, it doesn't have the glycerol as the backbone. Instead, it has the sphingosine. So it also contributes to the cell membrane, the lipid bilayer, and this is the sphingosine, which is having a C18 amino alcohol. An example given here, whereby the X group is replaced by hydrogen, and that's ceramide. So you have here various component or groups replacing the X. If it's only hydrogen, then it is referred as ceramide. Then if it's by phosphocholine, it's called sphingomyelin. And if it's sugar, doesn't matter if it's a single monosaccharide or a few monosaccharides, then it will be also referred as spingolipid. It also can have more complex oligosaccharide, as you can see here, made up of monosaccharide and also modified sugar. These are all the name of the groups. So here shown an actual example of this sphingolipid, which has the sphingosine as well as the X group that happen to be made up of the phosphocholine. So this is the X group, and then in order to know where is the C18 amino group, it is based on this structure here, okay? And the R group is the fatty acid. So this is sphingomyelin, which contributes in the making of cell membrane as well. So now you see the comparison between glycerophospholipid. So glycerophospholipid is this one here, because you can see the glycerol. Then you have also the sphingolipid. Since you can see the amino group, then that is the sphingosine. So both look alike and do have the amphipathic capability because of the charges that you can see for both. Therefore, they can play a role in being part of the cell membrane in terms of lipid bilayer. So here given the example, another example, cerebroside. So whenever there is a ending with SIDE, meaning there is a sugar present. So this is the sugar, the galactose, and the sphingosine is still present there, as well as one fatty acid. And this is also part of the structure and of the plasma membrane in terms of the outer leaflet of plasma membrane. Now we go to one more component of lipid, that is the sterol. But before that, we learn about these terpenes. These terpenes are a big group, and it composed of many components within it. In order to build these components for terpene, what will be the Lego unit is the isoprene unit. As shown here, isoprene having 5 carbon. These 5 carbon can be put together and build the other terpenes such as essential oil, vitamin, as well as these steroids or sterols, which will be the interest where we will learn about cholesterol as well as steroidal hormone. You also can build carotenoid. Carotenoids are found in carrot, the pigment found in carrot. So we learn more about what can be built by this isoprene. Of course, the isoprene does not just stay as 5 carbon. It's actually attached to 2-phosphate, normally by the use of ATP. So it will become isopentenyl pyrophosphate. And this will be, as a whole, the isoprene will be activated and reactive enough to form many other components as shown here. It can form the vitamins, ADEK, can form carotenoid, and it also can form rubber, the latex that we used to export in Malaysia. It's also come from this isopentenyl pyrophosphate. Other than that, you can also make cholesterol in the liver of a person, and from the cholesterol, it can become precursor or starting material to form bile acid, vitamin D, as well as the steroidal hormone that we're going to learn in a while. So next we look at sterols. Sterols also made from these isoprene units, and it is done in the liver of a person. So this is how the cholesterol structure looks like. Okay. It has these 4 fused rings, very rigid, and it's not soluble in water. Similarly, the hydrocarbon chain that is connected to it is also not soluble in water. So as a whole, this structure from here until here is not soluble. But this section here, which represented by the OH hydroxyl group, makes it like water. Therefore, it's amphipathic because of that OH. And then, been also mentioned here, it is the most abundant sterol in animal. It can be produced by liver. Also, you can get it from the diet. Food that is rich in fat seems to also bring in cholesterol. So the issue is for someone who has a problem in terms of removing the cholesterol, it will stay in the body and it will be deposited below the artery walls, and eventually when the deposit, which is called a plaque or arteriosclerosis, eventually it breaks, it will cause clogging of the artery, and if the artery turns out to be an artery found in the heart, then heart attack could happen, or they call it myocardial infarction. Okay, so now we talk about this steroidal hormone. So you always think hormone is made of protein, but in this instance, hormone can be also made by fat component. So you have the steroidal hormone, and they have function in regulating certain physiological functions. For instance, the male hormone, the testosterone, grouped as androgen. Then you have estrogen, grouped under it is estradiol. Then you have glucocorticoid or cortisol involved in monitoring or regulating carbohydrate in the body. They are all insoluble in water because they have that 4 fused ring, and therefore in order to be transported in the blood environment, blood is very water liking environment. Therefore these steroids that do not like water need to be bound to a protein and brought through the blood vessel. So we come to the one more component of lipid. I wouldn't say it's the last component of lipid. There is also some more others which we are not covering in this lecture. So here we have the fat soluble vitamin. But in terms of generally what are vitamins for, they are needed in small amount for good health of the body, and normally it cannot be made in the body, and it needs to be obtained in the diet. In terms of vitamin, it can be divided as fat soluble as well as water soluble. The fat soluble vitamin are the one referred as A, D, E, K, while the water-soluble one is B and also C. You would assume taking vitamin often actually good for health, but you have to be careful. If it's a fat-soluble vitamin, it could lead to something referred as hypervitaminosis, because fat-soluble vitamin could get deposited in fat and start to accumulate over the years. But vitamins such as B and C, being water soluble, even though in excess, they can then come out through the urine. So no problem in terms of B and C. So here, given the examples of the fat-soluble vitamin, that is A, D, E, K, with some description explaining each one. Vitamin A, obviously, it is useful to be seeing at night. If a lack of it or reduced amount, then you have a problem having night vision. And then vitamin D, as you know, you can build it by just going into the sun. Your skin can actually make vitamin D, and it is very much relevant in making strong tooth and bones. Then you have vitamin E, also known as tocopherol or tocotrienol. This is found quite a lot in our palm oil, and it is able to serve as an antioxidant. You know, antioxidant, you don't want oxidation of your protein, your carbohydrate. If it happens, then it could lead eventually to even cancer. And then you have vitamin K. Vitamin K is the one that changes fibrinogen to fibrin. That means it is important when you have a wound, you have a cut in your skin, blood could just keep on coming, but because of vitamin K, it can become fibrin, and therefore it can close the wound, and therefore no bleeding over time. So I end the first part of a lipid lecture by giving again another student activity. Actually, the lipid component does not end with vitamin A, D, K only, but there are also others, and this is the one, eicosanoids. Maybe you could research on it and find out that it actually involves in inflammation in our body, and it's also grouped as lipid.